Okay, so, ladies and gentlemen, yes, maybe I could bring them over to the light side. Okay, so maybe we'll stop. So here we go. Okay, so ladies and gentlemen, today we are going to have the first of what could be several lectures where we're talking about Spark support for machine learning. Okay, and this work will build on the skills that we acquired both early on within the class and in terms of functional programming and in terms of additionally skills from just recently in terms of manipulating data sources from Cassandra and in terms of manipulating data sets, data frames, and all that good stuff. So I'm going to send, to again decrease the amount of work involved, I'm going to be sending you this as well, because this will be a bit of a handful for you to type. So I'm just going to send that to you, and you may wish to also make use of that in your from your emails to sort of simplify the tasks here. Okay, the basic scope of what we're going to be doing today is conceptually straightforward. However, it's going to take a little bit of time to play out. So what we're going to be doing is we are going to be importing, and we're going to stop the SQL context. So we just started Spark. Do you remember why we do this? Under what conditions do we have to stop it?
Because you have to redefine it.
Yeah, we have to create a new one for Cassandra, okay, via the Cassandra connector. So we're going to stop that. We're now going after that, we're going to do a swag of imports, and I've just sent you those in your mail so that you can just copy them from the mail rather than typing them manually. We're going to do a swag of imports, and these imports are basically going to cover the different areas that we need to cover here. They range from Spark connector stuff to things having to do with machine learning and linear algebra for the machine learning, classification stuff, and some stuff involving data frames and SQL data manipulation and SQL. Today, we're going to look, as time allows, at several different machine learning algorithms for working with the data that we're going to draw from Cassandra, the data from these smartphones. Okay? The data collected from the smartphones cross-linked with survey data. And we're going to be using several machine learning algorithms to try to classify under what conditions people answer surveys or do not answer surveys, okay, using the Cassandra connector. Okay, this is going to be from a sample data set, but the same approach could be applied to many other data sets. So we're going to be, at a high level, going and grabbing survey data, going and grabbing sensor data, dividing each of those up into time slots, time bins as it were, and aggregating over those time slots. And then we're going to be linking, cross-linking them, so that we get the sensor data that was collected right around the time of people being posed with a survey. So we're going to have sensor data from a variety of sensors, including accelerometry, gyroscope, orientation, and it's going to be linked to the survey that was issued at that time. Okay? And then we're going to use these machine learning algorithms to look at this, to try to predict whether or not someone answered that survey, in fact. Yes, go ahead.
The purpose we would do this is so we can increase the chances that someone actually responds?
Well, down the road, we could use it to better time the surveys, yes, so that we issue them at times where people are not unlikely to answer them. For example, when they're driving.
Okay, we're trying to increase their response
That's
rate to the survey.
that's correct.
Okay.
Yeah, and try to explain to some degree why they're not answering them for cases where we have poor response rates. Are we issuing these things when they're in the middle of half a dozen things, in the middle of the day, etc.?
Question.
Yes.
For smartphone data, can we find out what apps they have open?
Yes.
Yep.
Ooh.
Well, okay, sorry. We have to be careful about that. Android is changing its standards for this. It used to be, and Kurt, in fact, wrote mechanisms to do exactly that, that you could say right now, what apps do they have open? Android is now preventing that from happening.
Okay.
And so what it's doing instead is, I think you could still find out which app is in the foreground,
Okay.
but you can't know the full apps that are running. You can get statistics on which apps ran in the past 24 hours.
Can you get a count of how many are currently active?
Not anymore.
Okay. That would be useful. I wouldn't think that would be that bad to have.
Yeah, but Android is banned it for privacy reasons now.
Well, I'm saying I don't
Yeah.
understand. I can understand not knowing what the apps are, but knowing you have 5 apps open is.
Oh, the total number open?
Yes.
I don't think
No.
it's valuable because the phone handles what apps are open.
Oh.
Like if you just switch out of an app, it decides when to close it.
Sure, but I was just pointing out that you could easily do a correlation between the number of apps they have open and the likelihood they have to respond to a survey.
Yeah, that's
You
true.
could use it as a proxy
Yeah,
for busy.
I
it's
don't know
just-
if that would be valuable.
It's just the things in the background. As Kurt says, it's kind of up to somewhat arbitrary rules from Android as to whether they're still resident or whether they evicts them. Like, in other words, it's pretty. It just does it to manage resources. It gets into the vagaries of resource management. How much memory does it have, and so on. So what you might end up finding is that the people with very few apps loaded predominantly are those with older phones or something like that. You know, in the sense that they have less resources. Anyway, let's go and start working with this. So I sent everyone here a copy of this, but I will type this out for the sake of our online users. So here we have to do pipeline and pipeline model. Actually, we're probably not going to get to that today. That will probably be on Thursday, that we'll be looking at Spark pipelines and the use of pipelines to define a series of processing steps. Pretty much everything here is going to begin with this org.apache.spark. So I'm going to actually copy this, which will make it quite quick to just issue each of these. .spark.ml.linalg.vector.
You could
Okay.
just show the screen and then people can pause it to see all the inputs if you wanted.
That's true. Did everyone receive the email?
Yeah.
Is there anyone who did not receive the email? One person. Okay, Hao has not received the email. Could someone forward the email to Hao?
Yeah. I think he's gonna get several forwards right now. I'll do it.
Okay, just break the symmetry. Someone do it and announce that they've done it. If you'd like, in a stentorian voice. Okay.
Done.
Okay. Rightly stentorian. Okay. Okay, here's, so I just did it down to here, and I'm going to do the rest of these by copy. Okay? Here we go. Okay? So what we've just done is we've just done all of these. Okay? Oh, phew. Phew. Boy, am I glad wrapping is not on. Do you see what I see?
A really long line with your password.
The password is omitted, though. Fortunately, it's just off to the right. Okay. Okay, so we are going to now go create a Spark conf here. So new Spark conf, and we are going to set the normal parameters. You've done this before in previous sessions. So you might want to copy it from that. Blinchiki .usass.ca .set spark Cassandra .auth .username Nate, and that's your username, and then we're going to set the password for that, right? So presumably password, all of you have passwords. Now at this point, I'm going to blank my okay, great. So ladies and gentlemen, we just created the conf with the username and password, and now we're going to go create a new Spark context based on this conf, the conf that we created using your secret information. Okay, here's our new Spark context. This is the whole reason we did sc.stop originally. We need to create a new Spark context. If you don't do that, it'll make this error message saying something like, you cannot have multiple Spark sessions running at the same time, and you may fruitlessly search your processes in your computer to find other instances of Spark running. But it's really because you're trying to use two contexts at the same time. Okay, and now we have one final import, which I could have said. Oh, no! Oh, God! Oh, man. Okay. 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 Okay, sorry. Import org.apache.spark.sql.sql context. Okay. And then we're going to go do val SQL context equal new SQL context SC. Okay, we're creating a new SQL context, and finally, sorry, one more import yet. SQL context dot implicits dot. Okay, we've done this before when we needed to query Spark, and that was Spark SQL for Cassandra. Okay. Okay, so we've got the boilerplate up front out of the way. Now we're going to define a few pieces of infrastructure, okay? One of them is a UDF, a user-defined function, which is, again, going to be lifted from operating on values to operating on columns by declaring it as a user-defined function. So this is going to take in a Java SQL timestamp. It's going to take in, the function as a whole is going to take in a column that operates in terms of that. And for each row of the column, it's going to map that to be the time to the bucket associated with time. So we're going to divide this up into 10-second buckets, okay? And so basically time is going to be quantized into 10-second buckets. This is number of milliseconds per second. 10-minute buckets, excuse me. This is number of seconds per minute. This is number of minutes. So we're going to be considering time in 10-minute chunks. So when we go to cross-link survey data, on the one hand, with sensor data on the other, we're going to be considering the 10-minute interval around the time when a survey was issued. Okay? And trying to use the sensor data from that 10-minute interval to predict whether or not the survey would be issued. Okay? Okay, next, I would suggest that you go and put in this this code here, okay? Basically what's going to happen is we're defining a method which takes in a key space and an Ethica table, and basically it goes and reads that table in using this load. So it sucks it in, or it actually creates a promise to suck it in. And then it annotates the data frame with a binning of the time slot. In other words, it creates a new column using this user-defined function that takes the existing column, record time, and applies this to it. So it creates a binned version of this record time. In other words, it indicates the 10-minute slot into which this falls. Okay? The 10-minute slot into which this falls. And it calls that time slot. Okay? Everyone should have that. So I assume that you forwarded both emails to Hal.
I did.
Thank you. Hal. Okay. There we go. So I just pasted that in. This is a very useful function that you may wish to use in many cases. So I thought, as I am wont, that I would create it.
That function basically we could replace the time time slot with anything else we wanted to bin, and we could apply that function to it.
That's true.
Actually, we should create a generic function that lets you do that.
That's correct. Yeah. Yeah. So I created this. I think it's going to be very useful. Next, we're going to use that information, and so we're going to do this. So we're going to create a data frame of survey responses, which is going to read from the survey responses table within this study, and it's going to bin it. So we're just using that function, right? There we are. And if we all hit this simultaneously, actually, because it's just a promise, nothing will happen. It will get really slow later. Okay. DF time slotted survey responses, okay? So this is a data frame. And if we go and we look at it, sorry, I meant to copy that. So this should be print schema, and we should get rid of this. And what we'll see is this is the data we've read, right? Or the data we will read. This is the metadata for it. So it has this timestamp, yes, but then it has this time slot. Okay, and actually we have this record time. This is the thing which we rendered using this user-defined function. We turned this record time slot, this record time field into a time slot. So this record time field was rendered into a time slot. Okay? Okay, now, just so you have a sense of what that looks like, I'll show 5 entries of this right here. And this is where it is going to be hitting the table here. But it looks something like this. So this is the time slot number, right? Another time slot, right? You remember that before we actually spent a while parsing these results. Remember that? We could actually figure out what questions they were and what were their answers to the questions. For single answer questions, for multi-select questions, I provided some machinery to do that to you. So it is here that we've provided a bit of machinery for manipulating these things. Okay. So if these methods didn't exist, it would be necessary to invent them. So I invented them. Okay.
Question.
Yeah.
The time slot number we have there, is that, that's actually like, if one time slot number is greater than the next one, that means it came after the first.
Correct.
Okay.
Correct. Yeah.
So we can reconstruct actual.
It's ordinal. Yeah. It's not merely categorical. It's ordinal. Okay. Okay, ladies and gentlemen, the next thing I'm going to do is, based on these survey responses, I am going to filter them down to be only for a certain user. And actually, do we need this? No, we don't need this. Oh, okay. We don't ignore that. Don't bother with that. I was thinking before that we'd focus on a user and survey ID, but we actually don't need to do that in this case. Before we did, because we were interested to look at the content from a very specific survey. We don't need to actually do this. Okay. And hence, all of these things can now be replaced in my code. So let's see. Here we go. All of these things can be replaced. Boom. Oh man, it must be off the bottom of the screen. Come on. Okay. All these things can be replaced by this. Boom. Okay, there we go. Okay.
One line, you probably want to delete them, right?
Yeah. Good call. So really all we want to do is to cache this. So this thing we just created, instead of doing this, we could just do cache it. Okay? Which will allow it to be held in memory, which will be useful for joining it. It will also be useful for some of the, unless we cache later results, will be useful for some of the machine learning. Ladies and gentlemen, machine learning is one of the big use cases that motivates a lot of the Spark architecture or design principles, in the sense that it's going to involve iterative algorithms running on the data many times over. We may see, before this session is out, algorithms that, for example, run logistic regression up to 100,000 sort of iterations on these records. And if they're on disk, it's a non-starter. I mean, it will take a very long time. If they're in memory, it could take place fairly quickly. And so keeping things in memory with caching is a big motivator for the use of the Spark architecture, rather than having to go back and recompute things each time. Okay, next. We are going to define another user-defined function, which we've defined before, ladies and gentlemen. It's this norm UDF, and we've defined it. If you grep in your past sessions, you'll find where you've done these before. This operation basically takes in values from a couple columns, and it basically determines the norm of them, the L2 norm. So it takes x squared plus y squared plus z squared, and it takes the square root of that. Okay. We're going to use this to collapse things that have an x, y, and z component into a single measure by taking their magnitude. Okay. We're going to be using this quite a bit. Okay, so this is this norm UDF. It's a UDF, and remember, as all user-defined functions, the function of a UDF is to lift things that operate on values so that they can operate on columns. So this UDF will operate on 3 columns. One consisting of x values, one consisting of y, one consisting of z. And for each row, it's going to take the x squared plus y squared plus z squared, the square root of it, and use that. And so we're going to create a new function that uses that. Okay.
So it allows us to collapse 3 columns into one.
That's, yeah, or define a new column based on those 3 columns, right. A new single column. Okay, the next thing we're going to put in is this other piece of code, other function which I sent you. Okay, and this function's job in life is going to be to basically aggregate a 3D data frame, one that has x-axis, y-axis, and z-axis values by user and time slot. Remember, time slots are these slots of 10 minutes each. We're going to aggregate it by taking the average of the norm over those x, y, z. And we're going to call that by some user-defined name. And then we're going to further take the average over each of those independently, x, y, and z, and give those names that indicate they're the x-axis, but also indicate the nature of the data. Because we're going to be working with cross-linked data where we have x-axis, y-axis, z-axis from an accelerometer, from a gyroscope, and from orientation. And we want to actually retain, we want to have a magnitude for each of them. So we're going to, for each of them, have a different name for the magnitude slot. And we want to keep track of the x-axis information in a way that gives the specific. So, ladies and gentlemen, that's what this function does. So this function is going to take in a data frame, and from that data frame, it's going to use the time slot information, the user ID, to aggregate things, and for each user and time slot, it's going to retain this information. Okay? Aggregate 3D data frame by user and time slot. Now, for this to operate, it needs to operate on a data frame that already has a time slot, right? And that was created by this guy up here, this function. So originally those were all in one function, but I split it out into two functions. Sometimes we may use one, not the other. So now what we're going to do is we're going to apply basically these two functions. This one to suck in the data and apply it and create time slots for it. This one to sort of aggregate up the data into those time slots for the X, Y, and Z and create these extra columns, these renamed columns. We're going to apply that now to the linear acceleration table. And then we're going to apply it to the orientation table. Then we're going to apply it to others. Okay? So that's what we're going to be doing. This one we're going to be calling with the name activity. The others will be calling with corresponding names. So for the accelerometer data, we'll get out something that looks like this. DF time slotted Excel KV. It's just going to be this later function applied to the results of this earlier function here. We're going to compose those functions. Boom. There we are. Let's go check what goes on. So we're calling, so this is how we called it. And I'm going to go, while you use that, I'm going to go print this out. Okay? Here we go. Okay? Now, a thought did strike me. I could send you all this code. Do you want me to send you all this code right now? Want or not?
Sure.
Okay, there we go. Well, okay, there's a certain thing I can't send you. Redacted. I don't, oh. Why did that suddenly wrap?
Because you turned wrap on in order to show us the other function.
I didn't turn wrap on.
I don't
Not
know.
deliberately.
You were showing
Maybe you
us.
turn it on when you replace something? I don't know.
Oh man, now I have to bother Muhammad again. Okay, well, as we say, the cat is out of the bag. Okay, so here we're going to go.
The fox has shown its tail, maybe?
No, that isn't a fox showing its tail.
That's not a tail.
I think the fox showing its tail was used for Lin Biao. So, okay, here we go. Actually, it wasn't Lin Biao. It was another figure, I think. Okay. Here's the code. And this is going to be, well, there's no use now. Okay. That's,
Remember the password.
Well, I know, but I said it's no use because it's already been betrayed. Now I'm gonna have to go reset it. Yeah. Okay. So that's been sent to you, so you know you should have access to that. Okay. Just don't use my password. Okay. Okay. So, ladies and gentlemen, coming back to this. Fortunately, the exposure to adverse attacks from outside the university, including for imposters sharing my name, is limited because it's firewalled, so you can't access it outside the university, that machine. You need a VPN. Unfortunately, I don't share my passwords with my VPN. Okay, so ladies and gentlemen, this time-slotted thing that we read in, remember here, after we get by the distractions, that we read in using this earlier function. We read in from the table, right? From the linear acceleration table, and we created the time slot. So basically, this guy got created using the time slot, the time slot here from this earlier function, this inner function, and then this outer function here. This outer function basically went and it aggregated things up to time slot by user. So this activity was the name for this normed combination of X, Y, Z. We called it activity here. We called it this name, which was the name we passed to it, activity, and this name here. And then it also aggregated up like the x-axis and called it x-axis underbar activity. So this is using the Krugerian invention, Krugerian delight of saying as this name.
I wish I invented that.
Interesting.
Yeah. Well,
Just found it.
it's a discovery anyway.
Are we sure we want the average of that?
No, but this is a teaching example, so it's fine. The point of this is not to do scientific research in this session. The point of it is to show the mechanisms by which we could do this. As far as whether we should, I think average is not a bad thing to start with, actually. It's not clear to me that there's a better option. I think it may be a suitable approximation.
Standard deviation, maybe?
I was thinking.
Not
Measurement of activity.
possibly standard deviation. I'd encourage people to think about that. But
Well, my concern is that if this is acceleration, then you could have areas where if you're in a car but you're stopped at a stoplight or you're going through downtown, I'm assuming we're gonna basically take this later and say if your activity is above a certain value or in the axis is of a certain value, then we think you're in a car. Okay.
But it's banned by time, so we'll be also looking at overtime, time bins.
Yes, but
well,
I'm just we'll see.
so here we've done a similar thing now for orientation. So before we had done this for activity. Now we're doing this for orientation. We're calling the norm the orientation mag, and we are labeling each of these guys here, the axes as well, as x-axis orientation. So let's do a print schema for this one, okay? So now we have these orientation data. This is the magnitude of the orientation as given by this one here. And then we have separate versions for each of these, okay? Okay. So, Amin, should I hold off asking Mohammed to change the password? during the session. Okay, so here is the average of the x-axis orientation over the course of that 10-minute interval. Y-axis orientation, Z-axis orientation. Okay? Okay. Similarly, we're going to do the same thing with gyroscope. Okay? Here we go. So here, we're going to get out of this. Oh. Oh.
That's weird. Did you paste instead of copy?
I meant to do copy, but maybe I'm puzzled by what happened because
Exited.
I'm aware that I exited. I'm not sure why I exited. I thought I did backspace. Sorry, I thought I did paste, but
It looked like you had paste.
yeah, I'm puzzled. Okay, so okay, we pause for this break. Okay, so I'm just going to go from the top and re-execute these things. You folks can use it to catch up if you're a bit behind. You can also use it to go retrieve the things from your mail if you need to. Okay, and now I'm going to do a paste. Okay, okay, here we go. Okay, and I'm doing the top of the head, so perhaps it's just as well I said pate. Okay. Okay. There we go. So catching up. We are reading in each of these things, right? So these functions basically allow us to read in the data, bin it, according to, or you divide things up into time slots, and then bin it up into components, okay? Tina, you can send mail to Dr. Wong and Song to get that data for patients specific to drugs, okay? I spoke with him last night. He was good with that, okay? They should be able to provide you a couple more noisified data. Noisified. We can't get the ethics data yet. Okay. Okay. So we're caught up now, okay? At least I am. Okay. So what have we done? What hath we wrought? Ladies and gentlemen, here we go. Just to remind you, here's our Excel data, divided up into time slots and users, joined, and then, you know, this is the aggregated magnitude, averaged over the time, and I agree that for that, certainly doing a standard deviation seems to be something worth thinking about, and I think I've spoken with some of you about that. And this is averaged for each of the axes separately. Particularly for orientation, the axis-specific information may be very interesting, because a phone that's like this or like this, you can assess its rotation this way in a way that may be more significant for whether someone answers the phone or not, compared to its rotation this way, okay, or rotation this way.
Possibly if someone's like on their phone, it'll be rotated this way as well.
Yeah, so something that's more vertical would be of interest. Its exact orientation this way isn't as much of interest, I think. Its axis relative to vertical is of particular interest. So this is one of the reasons we're preserving these things for our machine learning. Okay, so we've done this for Excel. We've done this for orientation. We have done this for gyroscope. Gyroscope. We also, to reflect on this fact, we have also done this for the time-slotted survey responses, have we not? Although it's not aggregated in the same way. Each of these is in fact classified as to this. So with the time-slotted survey responses here, time-slotted survey responses, what we did is we read them in with this column, but we didn't aggregate using this. With this guy here, we indicated the time slot with which it is associated. But we didn't aggregate it up to a time slot. We have each survey delineated, each survey issuance delineated separately as to the 10-minute time slot in which it lay. Okay? Are we comfortable with this idea? Okay. So we have all the sensor data delineated and aggregated up to time slot and user. And then we have, similarly, surveys delineated by time slot and user. And now, what's going to come next, do you think?
Machine learning.
Put it all together.
We'll put it all together, yeah. And before we do the machine learning, we're going to join it. So here, ladies and gentlemen, we're going to join it using two columns to join, user ID and time slot. Okay? And we're going to do this successively, joining in succession. Surveys to Excel, and then onwards to acceleration, and then on to gyroscope. Does that make sense? So the first of these, I actually kind of like this style of teaching where you don't have to type everything in.
Yeah.
You can copy. It allows me to explain more conceptually what's going on. Like or not?
Yeah. Like.
Okay, thank you. Okay, so ladies and gentlemen, let's just take the first part of this so we could see how this works. So here's this join. If I do a print schema here, what should I see?
Two together.
Well, you
The survey responses plus.
Yeah.
That's right. So here are the survey responses parts. And when do these come?
So joined.
From the other data set.
Yeah, the join data set from the accelerometer. And as each of these joins and non-heinous succession, the successive fields will be added onto here,
That's really neat.
right? Just added on one by one. Now, why is this occurring so quickly?
Because it hasn't
Actually
done the
evaluated
calculation.
yet.
It hasn't evaluated it yet. Yeah, exactly.
So I have a question though. Is this joining taking place on the server or on your computer?
It's a great question. Let me pose that to you. Is it taking place on the server or on our local machines? Where's the other work taking place? Where is the slotting taking place?
I think on the machine.
On your machine.
Yeah,
And this linkage is taking place on our machine.
that's good.
Or, I'm saying right now it's taking place on your machine. But when do you think, ladies and gentlemen, if Winchell were in charge of this enterprise, and if he had access to the fullness of the machines that stand before me, row after row, arrayed like a phalanx, if he had access to those machines,
In serried lines.
in serried lines, yes, beautiful. Ladies and gentlemen, if he had access to these machines, would this all be taking place on your machine? Where would it be taking place?
On each machine.
On each machine out there.
Except for join.
Those-
Well,
The joining actually could.
yeah.
You could actually have it partitioned so that all the data related to a given user and time slot are on a particular location out there. And so it doesn't have to match up everything with everything in a combinatorially heinous sort of match. It, in fact, is just going to have to deal with a smaller subset, okay? The smaller subset that's part of its bailiwick, its jurisdiction, okay? Its responsibility of a given machine out there might be a very small subset, or a given processor on a given machine might be a very small subset, if you partitioned it well, okay? So that's the plan, and you know, with access to those machines, we could do that. And I'll have it known that there's moves afoot to get us a small Spark cluster for use in our lab, and the work has been moving forward with it. there's there's some discussions about physically where the machines are going to be, but we have the machines right now. They sit upon a cart, not far from yonder desks. Okay. Okay. So, ladies and gentlemen, I in the midst of this soliloquy, I was partly motivated by the desire to allow this to play out. I was actually querying the data here. I was actually showing the data. And why was I showing it? Because I didn't want all of us to be executing at once, and from our advance to be limited by the time taken by all of you. So I'm actually playing this out. It's actually, what is going on here? Why is it showing these numbers?
Well, you asked for the first 2 rows.
Exactly. In order to do that, what does it need to do?
It has to join all the tables together.
It's going and joining the tables as we speak. So this is what's going on. And this is actually not a trivial operation, ladies and gentlemen.
That was what it had to do for the first record? Oh, the second record. Okay, that's not terrible. But it's faster the second time.
No, it's basically doing, I think it's doing essentially the full work here.
There's 6 stages, and it's just
Oh,
showing
I
us
see.
so many times.
Okay. It's just going
Yeah,
through stages.
yeah,
Okay, my bad.
yeah. So, so ladies and gentlemen, I did notice when I was working from home, believe me, it takes sometimes days to create each little class segment for this. When I was doing this at home, it's a lot faster to do from work. And also that CMPT 898 machine, to which, which has been set up for us, is actually quite a bit faster. I think because of the 8 cores available and the larger amounts of memory available, I find it considerably faster than doing it with my own machine. Now, mind you, that's compared to doing it from home, and I think some of that is network latency. Okay.
Do you have access to your activity monitor? I'd be interested to know if it's parallelizing it.
Good. Sure. Sure. So let's go here, and we'll do top, and you could see it running here. You're saying, is it running across multiple cores? Well, what can we do to see that? What can we do at the beginning of every Spark session if we were interested?
I would just pull up my computer's activity monitor.
Yeah, I'm Windows. I'm easy.
Well, there is a way to do that, in fact, but I think it's actually a more interesting learning exercise to do this. Right? Here are some jobs. Right? This is a job here. You could see these active stages of work. This has been going on for 2 minutes, right? And you could see sort of the
really
successive stages of the work, what it's going through in the
That's cool.
in the stage of the work.
Doesn't really make
I
sense.
think this
but it's
beats
cool.
the activity monitor.
That's awesome.
But you still haven't shown if it's parallelizing it or not.
Yeah, well, I think it's in here somewhere. So let's go poke around some more. Okay, so here are the successive stages at work. Okay, storage side. Okay, that's interesting. Would have expected that to actually have some environments. Okay, so the executors.
Cores 1, 1.
Okay, so.
They're using 1 core right now.
No, I don't think so. I think it's actually using 4, but let's yeah, it's actually using 4. I think these are the 4 cores associated with it. Okay, I don't know if I want to see a thread dump. Yeah, okay. How to read this for the core information. It does seem to be using 1 core now, but that may be, I'm curious why that is. Okay, so let's go look at accessories here, and where is the corresponding thing for the activity monitor here? I'm trying to remember. settings, system task manager.
Yeah, that's probably right.
There's another one beyond this that I think. Okay, so
Click on the thing by the graph.
sorry.
The upper left of the task manager, there's something that looks like a graph.
Yeah,
That would be
but
the
CPU. Okay, no. Show all processes. No. Hey. Okay. So.
I'll test it on my own, I guess.
Yeah, there is a task manager that's
System
better.
profiler. No, that's probably just something we have.
Profiler and benchmark. I think that's a more static thing. Okay. Anyway, back to this. Okay. So, ladies and gentlemen, let's do a schema here, right? Print schema. There we go.
Boom.
So here's all the data as it's been matched between these things. So one of the first things you should do, having gone through that, is what? Cache it. Let's cache this guy. I think we actually said to cache it previously, but that's fine.
Cache already cached data.
Yeah. Okay. Good.
So if you go cache before you actually calculate it,
Yeah,
that means that it's a promise to cache it.
that's correct. Yeah. Okay. Next, ladies and gentlemen, now we're going to be getting into the real machine learning time. All this has been kind of prep of linking these things up. Important prep, useful prep, necessary prep,
Exciting prep.
exciting prep. But
Lovely case classes.
okay, so ladies and gentlemen, the next task is we're going to classify. You may remember, I don't know if you will, but this duration, if we went and we looked at, how could we select just the duration column of this?
Dot. Oh, right.
Okay, so these are what the durations look like. Okay, what does 50 mean?
50 milliseconds?
50 minutes to answer that question. -1 indicates that it expired. I think -2 that it was canceled.
And 0 that
In any case, you can find that in some of these ones that we've done. So we're going to count basically both cancellation and expiration as being being 0. It's going to treat it as dichotomous. It's going to be 1 or 0. 1 if it was answered. In other words, if the duration was greater than or equal to 0. And then 0 for cancellation and for cancellation and for expiration. And any other value we're going to flag as a -1 and mumble.
Is there a reason why we're using 0 and 1 instead of like true and false?
Yes, because we need it to be numeric for the next for the machine learning.
Ah,
Yeah.
okay.
Okay,
Cool.
so you notice it says numeric response. And you'll find a different version of this function in some of my earlier code, which had labeled names. Okay, next. Okay, so the plates have been set. The table has been set. The plates have been laid out. And now, ladies and gentlemen,
We died.
we not just dine, young man, feast. Okay. Okay, so ladies and gentlemen, we are going to create, okay, so we're going to go through and we're going to create classifiers of various sorts here. Naive Bayes, logistic regression, decision tree, one after the other, in wondrous succession. Okay? But in order to do that, in order for them to be able to process the data in the Spark ML library context, the data needs to be in a certain format. And probably on Thursday in this very room, we will see how an earlier version of the Spark machine learning library called MLlib which operates on RDDs, resilient distributed data sets, directly, how that handles the data needs. There we make use of what are called label points. But the point here, labeled or not, is that we need to take the data that's in our data sets, data frames, this sort of data, this sort of data, and we need to put it into a format that the machine learning algorithms will understand, okay? They need to be able to grab the data from the sources in known places, okay? So they're going to need, among other things, a clear delineation of what the label is for the data, the ground truths. They're going to be performing supervised machine learning, so they need to know what the ground truth indication is. What is the ground truth indication here? For the thing that we wish to predict, what is the ground truth for it? What column holds the ground truth?
If they answered it?
Yeah, whether or not they answered it. It'll be the outcome of
Right.
this thing here. So what I'm going to do is, we're going to need to insert that classification as a column called label. Okay? And we're going to use that label column for our classifiers. It's going to know to take from the label column the label. Okay? Next, we're going to need, and this is where it may seem messy, but the beauty and the power of Scala is going to come back for us, or the framework they've created. And yes, it draws on Scala features here. Ladies and gentlemen, we are going to also need to place all features in a single column. There's going to be a feature vector. I believe that term should be of familiarity to you from your machine learning class, the notion of a feature vector. We're going to extract, ladies and gentlemen, a feature vector from this data that's going to consist of the features we want to match. And for one machine learning algorithm, it'll be a little bit different from another, it turns out. Some of the machine learning algorithms, like naive Bayes, for reasons unclear to me, for example, will only want non-negative values for their features. In other cases, machine learning algorithms will run on others. We may wish to experiment with different features, being able to classify based on different features in different cases. So we're going to create feature columns, each of which will combine within the same column all of the features of interest for a particular algorithm, okay? Or a particular run of an algorithm. Are we ready to steel ourselves to this challenge? Okay? Hearing no dissensions, I proceed. Let us proceed. Engage, yes. Okay, ladies and gentlemen, we're going to define a vector assembler. And this vector assembler is going to combine the data currently scattered among multiple columns into a single column. So we're going to tell the vector assembler, much as we will later tell machine learning algorithms, where to find the data on which it depends as input, and where to find the data into which it should place its output. Okay? Vector assembler. Do you see that? Ladies and gentlemen, in my youth, I served as a macro assembler. These days, I've graduated to vectors. Okay? Okay. So here's the vector assembler. Okay? This defines an assembler whose job in life will be to assemble vectors out of whole columns. Okay? So we're going to now apply that. We're going to apply to this join sensor data. And, okay, so mumble here. So this was, this is, okay, now why am I, okay, I'm confused though. Why is this called join survey sensor here? And then, okay, sorry, yeah, so it's join survey sensor. Someone misread it. DF join survey sensor. We're going to transform that with the vector assembler. Okay? And what will this transformation do you think? Well, let's transform it, shall we not?
Shall we?
Okay, ready? And I'm going to do print schema. Print schema. What got added here?
The features.
Features column, ladies and gentlemen. Features column got added. And that's a vector. So each element, each row of that contains a vector. And what information is in the vector, do you think?
Those.
Each of the data from that was originally scattered on that same row into each of these columns. So let's put it all into a vector.
But
All these 1, 2, 3, 4, 5, 6 numbers are now placed in this vector, in this vector column. You
What's
see?
the type of the whole thing?
Sorry?
The type of the whole thing, is it still a SQL context?
Oh, yeah.
or something?
Of this whole thing. Yeah. Yeah. It just
So there's an SQL type called
yeah,
vector?
it takes in a data frame and puts out here. I'll show it. It'll put out a data frame with that new column added. Nifty or not?
Yeah.
Okay.
It's nifty, but it seems like
Okay.
email requiring you to put this stuff to actually format your data correctly before it does that, and where MLlib doesn't, sounds like a step backward.
That it forces you to consolidate it there.
Yes.
Well, it simplifies the specification of the classifiers later. I agree with you. You could quibble with the design decision. No, it doesn't run faster. It's just it simplifies it a little bit in terms of the design. Okay, so we're going to now create not only that, we're going to assemble that with a label column that's going to delineate what? What would that label column specify?
Ground truth.
The ground truth. And how is that ground truth determined? Well, it's determined by applying this UDF, which says, okay, based on the duration, was it answered or not? It's going to apply that to the duration column, and it's going to call that column label. Do you see that? Yeah?
Interesting.
So this DF labeled, that took this output from transform and adds a label column whose contents is determined by applying this UDF to the data. Good or not? Okay. Ladies and gentlemen, let's run that. And that, ladies and gentlemen, will complete our assembly of the data requisite for several of these machine learning algorithms. DF labeled, print schema. There we are. We have features and a labeled column.
So, I mean, since we've moved all the other columns into features, we don't need any of the other columns.
We haven't moved all of them. We've only moved 6 of them.
We haven't moved all. We actually have only moved 6 of them. That's true.
But, I mean, you moved them so that they could be put in as inputs into the machine learning library. So why would you just create a separate
Why
structure?
wouldn't you?
Yeah, like a features label
Because
structure that
first of all, good question. First of all, this transform operates on a data frame and extends that data frame with that column. Now you could select it out and create a new column with just those. There's not a lot of advantage to doing that, and we may wish recourse to these other data when we're inspecting the outputs, like where it classifies correctly or not, or what have you. You could separate it out. You could separate it to a separate data frame. I don't see a really strong argument for doing that either. But here it's basically annotating. It's decorating this original one. Okay, so let's go create a decision tree classifier. This decision tree classifier, ladies and gentlemen. Okay. This is going to need some information about where to find the label and where to find the features for it. So this is the ground truth label. This is how it's going to judge. This is the feature vector, where it will find the feature vector. Notice that we haven't told it a data frame to operate on yet.
Right.
This is just saying, whatever data frame I give you, look for the features here and the label column here. We could have given it something else. We could have called it features 2, right? We could have so I'd called it my features.
But that's the name of the column it's looking for.
That's correct.
Feature vector.
That it will look for
It
which it will look in the fullness.
I have a really
Time.
dumb question.
Yeah.
What's a decision tree classifier?
So basically it creates a decision tree to try to classify. So it uses the information in the different columns and the ranges of that information to try to arrive at a decision scheme where looking at, using sort of predicate logic, looking at the value associated with this column, or with this feature portion of the feature vector, the value associated with this other. So in other words, looking at the orientation x-axis and y-axis, what their values are, and looking what the activity level is. Can it come up with a scheme that will specify the whether or not it was answered?
So basically, a decision classifier creates a decision tree that tries
Yes.
to classify things.
Correct.
Oh wow, that's interesting.
Provides a little algorithm in the form of a decision tree. So now, ladies and gentlemen, in the crescendo, we are going to fit this labeled data here using this decision tree classifier.
So this is just using a bunch of default parameters then for the classifier?
Correct. We're using default.
It has max.
Correct. We could specify all sorts of features for it. Okay.
Again, learning example.
Yeah. Exactly. Okay. Now, the interesting thing is, I would have expected this to show me some, based on my experimentation with. Here we go. So, ladies and gentlemen, what's going on here? Do you think?
It's fitting it.
It's fitting it. It's going over and over and over again and trying different schemes to fit this data, right? And this is not necessarily a quick process. Typically with a classifier, and we'll see this next time, it's going to have to be, because time is quickly depleting. We will see that you could specify all sorts of options for these classifiers. Of greater significance yet is we're going to be able to provide higher level constructs using the pipeline API and so on. We're going to be able to provide cross-validation machinery where it'll actually change some of those meta parameters, those higher level hyperparameters, as they're called in statistics. Okay?
7 nodes.
How many? It's 7 nodes. It's a little hard to see on the screen.
Sorry?
The screen's coming off on the left.
Oh.
So you can't really see.
Oh,
how many nodes there are.
Sorry. Does it need to be
Yeah, on the left.
foreshortened here? Okay. I think also though it's
Both, yeah.
sorry, I need to look at my screen, not the screen in the front. Oh, come on. This is a curious situation indeed.
Oh, that's 57 nodes.
57 nodes, depth 5. Okay?
That's so cool.
Can you just scooch it to the right
Can
now,
you move
please?
to a little to the right?
Yeah.
Just a little to the right.
Yeah.
Thanks.
Okay, there we go. Okay, ladies and gentlemen. Okay.
Cool.
Okay, next, ladies and gentlemen, we are going to go classify the data. Now, some of these classifiers, when you fit them, they actually remember their predictions for the training data, and you can go in and sort of compare it against. We're going to take this label data. We're not doing cross-validation yet. That will come in a later session. But here, we're taking that same data used for fitting just to sort of see how it classified it, right? And you'll notice that basically we have two things within that are notable within the ML framework. One class of things are estimators. This is an estimator. It knows how to estimate a model. We apply it to some data, it will estimate a model coming out of it. So we said, hey, fit a decision tree to this data. So this serves as an estimator. This guy, this model which came out, is a transformer. So we can apply the model to some data and it will give us some predictions, right? So here we are. And this is the data that came out of this transformation, which includes predictions. And we'll do print schema, and you'll notice that it has a prediction column. See that? It also has a probability column and a raw prediction column. This probability column is it's associated with the probability that this is 1 or 0, the probability that it's answered. A prediction column is, does it think it is 1 or 0 if it came down to it? Okay, so let's take a look at that. Time is a fleeting, so I'm going to just take a look at this. Okay, this is...
Can you show just the last two?
This is exactly. So let's go select label, probability, and prediction. Shall we not?
Sure.
Yeah.
Dot select.
Shall.
You're well spoken, young man.
For Chinese.
Prediction. Dot show.
Chinglish.
Okay. Here we go.
Wow.
Okay.
Not very certain.
Okay. So here you could see it thought. Okay. So remember, this last column is the prediction. So it thought these would be unlikely to be answered. They were in fact not answered. It thought these would be likely to be answered. It got many of them right. It missed these ones, right?
The probabilities are lists?
It's
What are
just
lists?
two
Oh.
of them.
It gives two. One is the complement to the other, the
Yeah.
probability of one thing versus the other, right?
So the 34 is the probability of false?
So
Yeah.
If you go down.
yes, I think that's right. Yeah.
That's why it's 1. That's why they predicted.
yeah.
True.
Okay, so we could show a larger amount if you wanted to inspect its
It's
performance
actually pretty
over a large. It's not bad. It's not bad. It's far from perfect, but it's actually pretty decent.
good. Can we actually just
So, well, let's go evaluate it. So we're going to create a binary classification evaluator whose job in life will be to evaluate the classifications from this and from other algorithms,
okay.
other classifiers. We're going to use it many times over for these other algorithms as well. So here's our binary classification evaluator. You notice some information it needs. It needs to know where's the label column, to know what the ground truth is. It needs to know what the raw prediction column is. And then it needs a metric by which to judge. And I set it to be area under the ROC curve. Have you learned about ROC curves for classifiers? Sorry?
Said in childhood.
In
Childhood.
In
I don't
820?
recall hearing them in 820.
In 820, you haven't covered them?
They might
Okay,
be in the book.
I'll explain them next week. They're an extraordinarily useful construct, actually. Very, very, very useful for reasonable classifiers. And they have to do with sensitivity and specificity and the trade-offs between the two. Okay? Because often you can get more sensitivity by worsening your specificity, etc. You could just say, in fact, this notion is not unique to me. I've heard it even the past day, that you could always just say, it's not going to be answered, right? And you may have a perfect case of specificity, but no sensitivity to detect when it would be answered,
These
for
are type 1
example.
and type 2 errors.
Yeah, you can have type 1 and type 2 errors, yeah. Anyway, we're going to evaluate this according to the area under the ROC, and here this is the area under the ROC curve. The maximum area under the ROC is 1.
Is this equivalent to saying it's 75? It's right 75% of the time?
No, it's not quite the same thing, but it's certainly related to accuracy, okay? So
But if you change the metric name, that could be one of the metrics you seek.
it supports several metrics for this. I think it may just be one more metric for binary classification evaluator, but I'd have to go look at the documentation. Okay, so ladies and gentlemen, here we've created a binary classification evaluator. We've created, big picture here, we've created a decision tree classifier, which is an estimator, something that knows how to, well, I should just show it in the code, I guess. This thing knows how to estimate decision trees, how to turn data, like training data, to arrive at a decision tree that best explains that training data. within the confines of its optimization algorithm. We then use that to take some data, which happened to be the same data we trained it on. We'll see later how we can do cross-validation. And we used it to instead to classify it. And then we compared the classifications, the label and prediction columns here, to see how well it did. And we declared an evaluator that could evaluate this according to a common metric, which is area under the ROC curve, this receiver operating characteristic curve. And here it has a sort of metric result that's actually not a bad metric. Now, there's a lot of things submerged here, and these are things we're going to get to Thursday. These include the parameters associated with it. These include what's the structure of the decision tree that comes out of it. How is it classifying? How many iterations is it running? And in fact, many of those things we could change. Many of those sort of things we could change. For example, the so-called hyperparameters and metaparameters used to estimate it, how many iterations it does. These are the sort of things that we might change. For example, let's go take this classifier. Remember, this is the estimator. It's the thing that knows how to estimate a decision tree. And let's go see what things we can set here. Well, some of them are things we're familiar with. The prediction column, the label column, things it needs to do its job. The features column.
Max bins is one, right, that you need to set? Max bins.
Max bins, yeah, exactly. Max depth of the tree, right?
In the middle.
The max memory to use. I think this min info gain might be associated with essentially when it converges, as it's trying to converge instances per node, etc. So, ladies and gentlemen, we could tune some of these parameters so that we arrive at a more suitable result. I'll just note here that that the results here may not be perfectly deterministic. For example, if we were to transform this data again, we might have to do the set seed thing here to change it. So maybe I'll do set seed. Set seed to be, 2, something like that. Okay, and here we're going to do. So I've just estimated a different model here using this, and I am going to create a second model which uses that. Sorry, what am I doing? What I meant to do is refit it, not to arrive at a new model. So here we go. So what I meant to do is to do decision tree classifier here. Boom. Oh no. Okay. Okay.
So
what I meant to do is to do a different classifier here, so I could compare the results. So this would be a different model, and it would be the same classifier, but with a different parameter value. So yes, Scott. Yeah. What's that? So here, ladies and gentlemen, with the classifier, we could do set seed to be, 2, and then do a different fit here. A fit, but with that different parameter. And we'll try this, and we'll see if it yields exactly the same results, right?
Because you haven't changed anything about the classifier's parameters. Just
Correct.
The seed.
Just the seed. So all I've changed is sort of the random assumptions it's using, the stochastics of its optimization, right? We could change the depth. we could change other things. Okay, so depth 5, 57 nodes. Looks like it's going to be pretty similar. We could reuse our evaluator here. So we could evaluate this time. Okay, wait a minute. No, we haven't applied it yet. We have to do this transform, right? Transform guy here. Boom, boom. Again, in some of these, okay, some of these ones, you actually you don't have to do the transformation explicitly. It's stored as part of the model. Here we go, and we'll evaluate this. Okay, this output and see if it yields the same. Yeah. So in this case, it's exactly the same result. It may have converged to the same tree despite a different seed. Not bad. It's actually pretty decent performance for this. So I think we're gonna let people go this time. Next time.
Next time, we won't let you go.
Sorry?
We're gonna let people go this time.
So
I think you meant at.
That's less funny.
we're going to next time create a logistic regression classifier, a naive Bayes classifier as well. And probably the time after that, we'll see how we can define a support vector machine as well. Okay. But in the meantime, you should have enough understanding that you could actually start applying this yourself. Okay. And meanwhile, I'm gonna frob this a little bit.
Get a new password.
I'll write to Mohammed about that. Set. I'm gonna do a set max depth. I'm gonna increase the depth of this to be.
That's 5, right?
Now it's 5. I'm gonna do it to 7. Okay. And oh, okay. I should have really done this with a separate one so I could compare the results more easily. Okay, here we go. Boom. Ah.
You're doing on the original one.
Okay, I'm doing on the original one. I don't know why it's copying it with the. Okay, that's why. Yeah, so I'm gonna do it with this. Come on. Yeah.
We're also excited.
Yeah, I know. Well, with good reason.
This is pretty quick, actually.
It's not bad. It's not bad. And this is what requires this multi-passes. This is a lot of what motivates the caching and the sort of in-memory parsimony associated with this. Okay, so here we're going to go. Okay, and this would be the decision tree classifier 2, or sorry, 3 that I just defined here. And I'm going to.
You'll get the same one, but that's fine.
Do you think so?
Yes, because you called the last time you ran this was the one decision tree model trained on complete data that you ran, and that was the one you accidentally remade to have set max.
No, but he's got the classifier up top 3, set max at 7.
Yeah, but there's a line above it that says decision tree classifier equals.
Oh, does it?
I
Okay.
believe so.
Oh, yeah. I see what you're saying. Yeah. So no wonder it's actually taking a little bit longer to actually do this.
Well, but the interesting part is that not only
Okay.
do you have higher depth, you also have more nodes.
Exactly. Yeah. Okay. So
191 nodes at 7. That's a really complex tree.
it's a complex tree. Okay. Let's go see if the complexity has led to commensurate predictive value. Shall we not?
I doubt
Well,
it.
predictive value, I mean, it's not cross-validated, so it could be overfitting.
Oh, yes, and we'll be taking a look at that probably next time. So let's do this. So here's our model that we just created with depth 7 instead of depth 5, and we are going to transform the same data. And sorry, this is a classifier, and this is the DF. Yes, this is the data set predicted by that model, DF labeled. Okay. This. Here we could, once again, we could go paste here, and we could do select, label, and prediction, right? And show that, for example. And inspect it. This is not too bad there, not too shabby. We could do it for a longer series there, and we'll see some mistakes for sure. But it's got
It seems.
it has some misses for sure, but it's capturing some big patterns. Let's go evaluate this thing.
Well, I'm interested in whether or not it's biased. It looked like it was biased towards 0.
Okay.
But we'll see.
It may be. So here we are. It's going to evaluate it for the ROC curve. 75. It's actually
It's slightly
bigger,
Was the other one 74?
but
77?
not.
It was 0.746
too much better.
before.
Yeah. It was
74?
just short of 75.
You basically triple number of nodes and add 2 entire things to get
1%.
0.006 increase in your
Yeah,
area of the ROC.
That's exactly right.
That's called not worth it.
Yeah. Yeah. So if there's a parameter that we should change, it doesn't seem the depth one is going to help, at least within the scope of our sort of evaluation, the scope of our training.
I would actually go the other way. Is how shallow can you get the tree
Without.
sacrificing
Yep.
area. But
Okay.
Not it.
Okay, good. Thank you, folks, for coming. And next time we are going to look at some additional classifiers, including some that have different needs, some gotchas associated with them. We may also get into a bit of the cross-validation next time, or that may need to wait till Tuesday, okay?
Thanks.
Okay, very good. Thanks for your attention.